Hi everyone, welcome to NEETshala Organic Chemistry Lecture Series Part 2. In this part, we will be discussing about alkenes and alkynes. So let's get started with alkenes. First, let us study about the preparation of alkenes. We can prepare alkenes from a variety of compounds such as alkynes, haloalkanes, vicinal dihalides, also from alcohols and carboxylic acids. So let us see what are the different methods of preparation of alkenes. First method of preparation is from alkynes. How can we prepare alkenes from alkyne? We have two different reagents to study over here. One is known as Lindlar's catalyst. Now, what is Lindlar's catalyst? Lindlar's catalyst is basically palladium in the presence of carbon or quinoline. Quinoline, which is basically a sulfur compound, are poisons, which is deactivating the charcoal. And this is used for the preparation of cis-alkene from an alkyne. So if we are treating alkyne with Lindlar's catalyst, we will be getting a cis-alkene, matlab hydrogen will be substituted to the same side of the plane. And we have another reagent which is sodium in the presence of liquid NH3, and this will give us trans-alkene, and this reaction is known as Birch reduction. This reaction is known as Birch reduction. So we have to remember this in mind, that Lindlar's catalyst will give us cis form and Birch reduction is going to give us trans form. So now let us move on to the second method of preparation, that is from alkyl halides. Now whenever we have an alkyl halide such as these, and if we are treating it with alcoholic KOH, which is also known as alcoholic potash, so at that time what is happening, a process which is known as beta elimination is going to happen. Now what is beta elimination? As we know, the carbon to which the main substituent is attached is known as the alpha carbon, and the carbon which is just adjacent to the alpha carbon is known as the beta carbon. Now what is happening is that when we have a halo acid like this, a halogen acid like this, beta elimination will happen. Now what does that mean? One of the substituent, that is the major substituent from the alpha carbon, and one of the substituents from beta carbon will be removed off, leaving behind two free radicals, and these two free radicals are going to join to form a bond, and we get an alkene. So what is the mechanism of dehydrohalogenation? Dehydrohalogenation means from the alpha carbon we have to remove the halogen, and from the beta carbon we have to remove a hydrogen. So this is the process of dehydrohalogenation, and dehydrohalogenation is an example for beta elimination reaction, which is followed through free radical mechanism. Now let us see some important note over here which is given in NCERT. We can get the order based question from here. What is that? First one is the order of reactivity of halogens towards beta elimination reaction. It is iodine, then bromine, then chlorine, and least is fluorine. And when we consider the alkyl group, the reactivity of the alkyl group towards the beta elimination reaction is following the order tertiary, followed by secondary, and finally we have the primary. So this order is important for exams. Now let us see the third method of preparation, which is from vicinal dihalides. Now how can we prepare alkenes from vicinal dihalides? Here, what are vicinal dihalides? Vicinity means neighboring positions. So in the neighboring positions, we are having halogens substituted. So when we are treating it with zinc metal, what is happening is that these two halogens are removed off, and that is going to join with the zinc to form ZnBr2. Again we are left with free radical over here and also a free radical on the carbon, second carbon. So between the free radicals of the first carbon and the second carbon, there is formation of a double bond. So that will result in the formation of an alkene. So we can say that dehalogenation is a process which is used for vicinal dihalides because we have to remove two halogens, and it is also following free radical mechanism. Now let us see the next one, which is from alcohols by acidic dehydration. Now acidic dehydration, what do you mean by dehydration? Dehydration means it is the removal of something. D means removal and hydration, so it is removal of a water molecule, and this is carried out in the presence of H plus. It is carried out in the presence of H plus, that is why it is known as acidic dehydration. Now what is happening if we have an alcohol of the formula CnH2n plus 1 OH? If that is the alcohol, what is happening? One of the hydrogen from this part is moving out and the OH is also moving out. So what is happening? We get an alkene of the formula CnH2n. So I will write a general reaction for this. So we have CnH2n plus 1 OH. This is undergoing the process of acidic dehydration to give us CnH2n. So we are eliminating a molecule of water. OH is coming from this side and one of the hydrogen is coming from the alkyl part. So this is an example for acidic dehydration, and again acidic dehydration is also an example of beta elimination, where OH is moving on from the second carbon and hydrogen is coming out from the first carbon. So let us see the example here. Here we can see the OH on the alpha carbon, and this OH is removed out along with the hydrogen in the adjacent position, that is in the beta carbon. So these two are removed, resulting in the formation of free radicals here and here, and they are going to be joined with another single bond, so we get a double bonded compound, that is ethene. And what is the reagent that is commonly used? We are using concentrated H2SO4. It is a strong acid. With this, we complete the preparation. We have already studied the preparation of how we can prepare alkenes from carboxylic acid. So comment below which is the carboxylic acid which is used for the preparation of ethene. Now let us move on to the physical properties. There is not much thing to discuss in physical properties because the physical properties of alkenes are comparable with alkanes. So let's just go through this and let's see if there is any important stuff here. Alkenes as a class resemble alkanes in physical properties except in the types of isomerism and the difference in the polar nature. First three members, that is C1, C2 and C3, are gases. Next 14 are liquids and the higher ones are solids. So we have to study which are the gases. We have ethene and propene. Also we have butene, these are the gases, and then we have the liquids, and from 15 onwards we have the solids. Ethene is a colorless gas with a faint sweet smell. All other alkenes are colorless and odorless. So every gases are colorless and ethene is an exception because it has a faint and a sweet smell. Now they are insoluble in water but are fairly soluble in non-polar solvents like benzene, petroleum, ether, like we have studied yesterday, like dissolves in like. And they will show a regular increase in the boiling point with increase in the size, that is every CH2 group added increases the boiling point by 20 to 30 Kelvin. Like alkanes, the straight chain alkenes have higher boiling points than isomeric branched chain products. So like we studied yesterday, boiling point is directly proportional to the number of carbon atoms and it is inversely proportional to the branching. The same thing is followed here also. Let us now move forward to the next part, that is the chemical properties. Now the reactions of alkenes are basically divided into four categories. First one is addition reaction. In addition we have electrophilic addition and free radical addition. Very rarely it will show substitution reactions as well. We have oxidation, ozonolysis and substitution in this chapter. So let us start with the most important reaction, that is ozonolysis. Now what is ozonolysis? Ozonolysis is a process of addition of ozone molecule. So we are adding ozone molecule, that is O3, into an alkene. This will result in the formation of an ozonide. So let us consider this as a hut, or we can say this is a home, and these people are going to destroy every homes. So these are our terrorists. So these terrorists, that is zinc and water, they are going to destruct the home. So we can say home is our war zone. So what we need to do is, first we need to create a home. How can we create a home from an alkene? We can create it by adding of ozone molecule, and once we get the home, we are going to destroy the home by using a terrorist. And who is the terrorist? It is zinc and water. We will get some new homes, and whatever remains or remnants of the terrorists attack was there, that we are going to remove, and we are going to create a bond between the remaining. We're going to create a bridge in between all the unwanted stuffs here. That is what we are doing in the process of ozonolysis. So let us do the process. Let us take an example for ozonolysis. If we have CH3, CH double bond, CH2, we are going to add oxygen. So we will put one oxygen at the top of double bond, one oxygen just below the carbon on the left side, and one oxygen just below the right side carbon. And we will just join the bonds like these. We will create a hut, and now we are going to add zinc and water, as a result of which what is happening, there is a cleavage of bond that is happening like this. From the roof to the base the cleavage is happening, and now we are getting two different compounds. Now we will put a double bond here, so we get CH3CHO, which is an aldehyde, and we are getting HCHO, which is methanol, again an aldehyde. So we have got two aldehydes over here. So this is the process of ozonolysis. Let us take another example. This is 2-methyl propene. 2-methyl propene is undergoing the process of ozonolysis. So here also we have to put the oxygen one above the double bond, one below the left side carbon, one below the right side carbon, and form an ozonide. And here we have a CH3, and here we have a CH3 again. We are going to cleave the bond from the roof to the base again, and here we have a ketone. So if we have 2CH3 attached to the carbon onto which the double bond is attached, then there is a possibility that we get a ketone. So here we are getting a ketone, and the other one is going to be an aldehyde. Right, the other one is going to be an aldehyde, and on the left side we have a ketone. So that is why we have HCHO, which is an aldehyde, and this particular ketone is also formed over here. Let us move on to the next reaction. Now let us move on to the next reaction, that is the addition reactions. First addition reaction that we are going to discuss over here is the addition of dihydrogen. So if we have to add dihydrogen, we can use platinum or palladium or nickel. So when we are adding hydrogen by using platinum, palladium or nickel, we get alkane. And if we are doing the same reaction on an alkyne, then we will be getting an alkene initially, and again on hydrogenation we get an alkane. Now let us move on to the addition of halogens. Halogens ka matlab dihalogens, that is X2. So when we are reacting it with X2, what are we getting? Let us see the reaction. We are using carbon tetrachloride as the medium for the addition of dihalides. So one of the bromine is going to be adding to one of the carbon, and another bromine is added to another carbon, so we get a vicinal dibromide. And now let us move on to the next compound, the addition of the next compound, which is hydrogen halide. Now hydrogen halide, when we are adding, we have some conditions. What are those conditions? If it is symmetric alkenes, it is okay, we can add it in any fashion. Hydrogen towards one side and bromine towards the other side, like this. There is no problem for that, and even this is an symmetrical alkene. So in the case of a symmetrical alkene, we can put hydrogen on one side of the double bond and bromine on the other side, because even if we read from the front side or even if we read from the opposite side, it is the same. So that is the reason why there is no problem in the case of symmetrical alkenes. But what happens in the case of unsymmetrical alkenes? Let us see. In the case of unsymmetrical alkenes, if I put hydrogen over here and bromine over here, I will be getting a compound like this. And if I am putting hydrogen over here and bromine over here, then I will get a compound like this. Now the problem is, which of these is the major compound and which of these is the minor compound? How do we judge that? For that, we have a rule which is known as Markovnikov rule. So let us learn a very interesting story of Markovnikov. Markovnikov, let us consider that he is the villain of our story here, right? So he is a very rich person and he does not want any poor person to become rich. For that, what he is telling, if he is the king of any country, he will say that give the poor all the burden and make the rich much more richer. This is what he said through the rule which is known as Markovnikov rule. Now the country is organic chemistry and the people are the alkenes. So let us take an alkene to understand what is this particular rule. If we have CH3 single bond CH double bond CH2, we can see that this side of double bond is deficit of hydrogen because it has only one hydrogen, and the other side, that is the right side, is having two hydrogen. So which is the poor side and which is the rich side? This is going to be the poor side and this is going to be the rich side. Now according to Markovnikov, we have to add the H to that side which is excess of hydrogen. That is, hydrogen should be added to the right side and substituent should be added to the other side, which is the poorer side. This is what is known as Markovnikov's addition. Now the most important thing is the mechanism of Markovnikov's addition. Markovnikov's addition follows carbocation mechanism. Now what is that mechanism? Let us learn about that now. Let us first dissociate this HBr. It is not going to give us hydrogen free radical and bromine free radical. Rather, it is going to give us H plus and Br minus. Now, first let us take the carbocation. First we have to prepare a carbocation and then only we can substitute the negative part, right? So first let us create the carbocation. For that, let us treat the alkene with H plus. And when I am treating the alkene with H plus, two possibilities can be there. Either we can substitute it on the right side and get a primary carbocation, and another possibility is that we can substitute it on the left side and we can get a secondary carbocation. And as we know, the secondary carbocation is more stable as compared to the primary carbocation. And since it is more stable, we will follow this one and not this. So to this we will add the Br minus. So the bromine will substitute to the second position and it is going to be the stabilized product. So we are getting 2-bromopropane as the major product, right? So now let us move on to anti-Markovnikov's addition, also known as peroxide effect or Kharash effect. Now always remember, Kharash effect or peroxide effect will happen in the presence of a peroxide. And this Kharash is a very good person. He wants the poor to become rich and rich to become poor. So what is happening? We have to add hydrogen to that part which is deficit of hydrogen, and the substituent should be substituted to that part which is already having enough of hydrogen. So let us see a mechanism. Let us take benzoyl peroxide. Let us take benzoyl peroxide. This is an organic peroxide, and we are going to undergo the homolysis, and we will be getting free radicals. Benzyl peroxide के free radicals मिलेगा, और we are going to remove this carbon dioxide molecule to get C6H5 free radical and CO2. Now two such C6H5 free radicals are formed. One of these is going to react with an HBr to form C6H6 plus Br free radical. Now it is this Br free radical that is going to attack onto the alkene. So can I say that this benzoyl peroxide is a free radical generator? Yes, it is a free radical generator which helps in the generation of a free radical, that is Br free radical. Now this Br free radical is going and substituting on the alkene, and now we may get two different products. One is a primary free radical of alkene and another is a secondary free radical. Now as we know, secondary is more stable, so we are going to substitute the H plus over here, because bromine already gets substituted first and then only a hydrogen is moving. So now we are getting two products here, and here one is secondary secondary free radical and another is a primary free radical. And since secondary is more stable than primary, we are going to react that particular free radical with another molecule of HBr to give us CH3 CH2 CH2Br. That is the final product. So what we have to remember over here, the most important thing to remember is that in Markovnikov's addition we are following carbocation mechanism, and in anti-Markovnikov's addition we are following free radical mechanism. And what is the conditions for anti-Markovnikov addition? We have either H2O2 written at the top, or we have organic peroxide like benzoyl peroxide. Now let us see what is a question, what is the type of questions which we can expect over here. Now we don't have to write the mechanism every time for questions like these. Suppose we have hex 1ene, that is CH3 double bond CH2, that is going to be repeated 3 times, and finally we have CH3 6. Yes, so we are going to add HBr according to absence of peroxide, that is anti-Markovnikov's addition. So this is the poor side and this is the rich side, poor side and rich side. If we are not following the Markovnikov's addition, we will add the substituent over here. This is CH2, so we will add the substituent over here. Br is added to this side and hydrogen is added to this side. And if we are following Markovnikov's addition, then we will add the substituent over here and we will add the hydrogen over here. So this is about the Markovnikov's and anti-Markovnikov's addition. We have another examples of this as well. One is the addition of sulfuric acid, and we can also add sulfuric acid in the same method. We are taking H plus and HSO4 minus. This HSO4 minus is adding to the alkene by again Markovnikov's addition. Addition of water is also in accordance with Markovnikov's rule, where we have H plus and OH minus. So this OH minus will substitute to that side which is having less hydrogen. Now moving on to the next reaction, that is oxidation. So now let us discuss oxidation. In oxidation we have to remember a reagent which is KMNO4. Now KMNO4 can be dilute, it can be concentrated. First we are going to take dilute KMNO4, which is basically cold dilute aqueous solution of potassium permanganate, is known as Bayer's reagent, and this Bayer's reagent is used for the test of unsaturation. How can it be used for the test of unsaturation? Is because this is changing its color. It will fade the purple color, and as a result of which the purple color solution which we have initially is going to be changing to a colorless solution, a faint colorless solution. So let us take an example. We have CH2 double bond CH2. We are going to treat it with dilute KMnO4. At that time, what is happening? If we have dilute, we are going to get diol. So we can remember it like this. Dilute gives diol. So we will get ethane 1,2-diol, which is also known as glycol. Now let us take another example, CH3 CH twice CH2. Sorry, CH3 CH double bond CH2 plus dilute KMnO4. What is it going to give? To this position also we get an OH, and to this position also we get an OH. So it's a very simple fact that if we are using dilute KMnO4, we will be getting a diol. So I will write that trick here. Dilute gives diol. Now let us see what happens in the case of concentrated. In the case of concentrated KMnO4, or in the presence of acidic potassium dichromate, what is happening is that the alkenes are oxidized to ketones or even to acids depending upon the nature of the alkene and the experimental condition. Like over here we have substitution of methyl groups on the carbon. So whenever we have methyl groups, more than one methyl groups which is substituted on a carbon, there is a possibility of ketone. And the other part which has just a hydrogen, that is going to give us carbon dioxide. And in the case of but2-ene, what is happening is that this part does not have any substituent, like two substituents of carbon is not present anywhere. So here one of the substituent is hydrogen and another is CH3. So what is happening, this is going to cleave like this, and this side is going to get oxidized, double oxidized, so it is going to give us CH3COOH. Now how to do this type of problems? We have a short trick for that. If we have substituents like this, two alkyl groups which are substituted on the carbon, that is going to oxidize to give this, that is ketone. On the other hand, if we have one of the hydrogen and another is a alkyl group which is added to the double bonded carbon, then we will be getting carboxylic acid. And if we simply have an alkene, then it is oxidized to carbon dioxide. So this is an important memory aid which will help you in solving the questions related to addition of KMnO4. Now let us move on to polymerization. Now polymerization is a very simple process. We have to just create a chain of monomers. A chain of monomers is going to give us polymers. The same reaction we will study in the chapter of polymers, and polymers is very important because it will help in preparation of many of our day-to-day needs. And some conditions are also given here: high temperature, pressure, and catalyst. The catalyst which is used is this, plus C2H5 thrice plus TiCl4. This is going to be the catalyst which is used, and the name of this catalyst is Ziegler-Natta catalyst. So now let us move on to the part of alkynes. Now first we are going to discuss about the structure of alkynes. We know that alkynes have a triple bond. Triple bond means we have one sigma and two pi bonds, and these two pi bonds are mutually perpendicular to each other. One is aligned along px axis and another is along py axis, as a result of which we will be getting two mutually perpendicular pi bonds. The electron cloud between the two carbon atoms is cylindrically symmetrical about the internuclear axis, and the structure is a linear molecule. We have to remember the hybridization. Hybridization is sp hybridization. We won't get questions based on this, but just remember the strength of carbon-carbon bond. It is 823 kilojoule per mole, and that is more than that of carbon double bond carbon and carbon triple bond carbon. Sorry, carbon single bond carbon. So this is the important fact. And another important fact is the hybridization, that is sp hybridization, and the number of pi bonds and the number of sigma bonds. Pi is 2 and sigma is 1. This is what we are supposed to know from this particular topic. Now let us see the preparation. We can prepare it from calcium carbide and from vicinal dihalides, from alkyl halides, Kolb's electrolysis method. So let us see it one by one. First method of preparation of alkyne is by the hydrolysis of carbides. So if I take calcium carbide is hydrolyzed to give us ethane. And remember here there is two carbon in the carbide, so we will be getting an alkyne with two carbon. And if I am taking a carbide with three carbon, as you can see over here, then we are going to get an alkyne which is having three carbon. So this is the trick that we can remember. If we have a two carbon containing carbide, we will be getting an alkyne with two carbon. And if we are taking a carbide with three carbon, we will be getting an alkyne with three carbon. Next is dehydrohalogenation of dihalide, that is this. So what are we going to do? In the first step, we are going to remove an HBr such a way that we are going to remove this bromine and hydrogen from here in the first step. And in the second step, we are going to remove bromine from the first carbon and hydrogen from the second carbon. That means we are carrying out two steps of beta elimination or two steps of dehydrohalogenation, and that will result in the formation of alkene. Now, dehalogenation of a tetrahalide. We are removing these two Br2 again by the process of dehalogenation, that is again a beta elimination method, and doing it twice by using zinc, we will be getting alkyne. Another is from alkyl halide. We can react the sodium salt of alkyl halide with another alkyl halide. Sodium salt of an alkyne is reacted with alkyl halide to give us NaX is also removed out, and we will be getting RC triple bond C single bond R. The last method is Kolb's electrolysis method that we have already studied. If we have a dienoic acid, the salt of this dienoic acid on electrolysis will give us alkyne. And another example is given over here. We can directly convert it into alkyne from carbon, that is by using an electric arc at a very high temperature of 1475 Kelvin. So these are the different methods of preparation of alkynes. The most important ones is the first one, and also the Kolb's electrolysis is very important. These two are the most important ones. And since NCERT also mentions vicinal dihalide, so this is also an important and an easy method. Now let us move on to the physical properties. Again, the physical properties of alkynes follows the same trend as that of alkanes and alkenes. First three members are going to be gases, next 8 are going to be liquids, and the higher ones are going to be solids. All alkynes are colorless. Ethine has a characteristic odor. Other members are odorless. Alkynes are weakly polar in nature. They are lighter than water and they are immiscible with water, but they are soluble in organic solvents like ethers, carbon tetrachloride, and benzene. Their melting point, boiling point, and density increases with increase in molar mass, just as we have seen in the case of alkenes and in the case of alkanes. Now let us move on to the chemical properties of alkyne. The first one that we are going to discuss is the acidic nature of alkyne. So here let me take an example to illustrate this. If we are reacting NaNH2, which is a strong base, NaNH2 is a strong base, so when it is reacting with C2H2, it will liberate hydrogen gas. It will liberate hydrogen gas. So this particular reaction indicates that this C2H2 is acidic in nature. This will indicate that it is acidic in nature. Now, this is one explanation for acidity of alkyne. Another explanation is by the percentage as S character. Now, how do we predict the percentage S character? Let us see. Let us calculate over here. We have the hybridization of C2H2 as sp hybridization. Sp hybridization means there is 50% S character, which is very high as compared to that of sp2 and sp3. Since it is very high as compared to sp2 and sp3, this is going to be the most acidic group of compounds. So we have an acidity order here. This is the acidity order. So we can see that more the S character, more is the acidity. So if we are asked to compare the acidity of different compounds, like the one which was asked in 2017, what we have to do is step number one is take out the hybridizations. More the S character, more is the acidity. This is the first comparison. And if we have two compounds which is having the same hybridization, then lesser the number of carbon, more is the acidity. So this is the important point to note. Acidity is directly proportional to hybridization, or we can say percentage S character, and it is inversely proportional to number of carbon. So this is the most important point. Using this, we can solve any questions related to acidity orders. So let us see the reactions also. The reaction is, it is reacting with sodium and also sodamide. The same reaction is going to give us. So that is going to give us monosodium ethanide, and also we will get hydrogen gas, like we are doing with any of the metals, right? If we have sodium and sodium is treated with any acid, it will give us hydrogen gas plus a salt, right? So here also the same mechanism is followed. We have sodium and we are going to treat it with C2H2, then it is going to give us CHC triple bond CNA plus hydrogen gas. So the same reaction is happening in both cases. The analogous reactions is happening in both cases. Hence we can conclude that alkyne is acidic in nature. Now let us move on to the addition reaction. Again, the same mechanism is followed over here. We have Markovnikov's rule applicable in the case of alkynes as well. Let us see the addition of dihydrogen. Again, the catalyst used is platinum, palladium or nickel. So in the first step, we will be getting an alkene, and now we have to carry out the hydrogenation in alkene to get an alkane. Coming to the addition of halogens, we can add it in the first step to get a substituent like this. We will get an intermediate like this, and again on treating it with Br2, we will be getting a tetrabromopropane. First we got a propene, and again on halogenation, or we can say again on addition of halogens, we will be getting tetrabromopropane. And now we have addition of water, and this is a very important reaction. We had nearly 3 to 4 questions in the past years, so this is very important. We have to treat the alkyne with water in the presence of Hg2 plus and H plus at 333 Kelvin. So when we are doing the following conversions, what is happening is that the OH will be substituted to that part which is having lesser number of hydrogen. Okay, so here, as we know, it is a symmetrical alkene. Since it is a symmetrical alkyne, so we have no problem. We can add H to one side and OH to another side. Then it will undergo keto-enol tautomerism, as a result of which it is going to form the keto form, that is this. Here, if I consider another example, which is an unsymmetrical alkyne, what we have to do? First step is we have to add hydrogen to that part which is having excess of hydrogen, and OH to that part which is having deficit of hydrogen, and then we have to carry out the keto-enol tautomerism, and as a result of keto-enol tautomerism, we are getting a ketone. So if we have hydrogen, then it is going to give us an aldehyde, and if we have methyl groups on both sides, we will be getting a ketone. Now we have polymerization. Polymerization is of two types. We have linear polymerization to give us compounds like polyacetylene. If we have C2H2, this one polymerization will give us polyacetylene. And cyclic polymerization is carried out in the presence of red hot iron tube. This is going to give us benzene. So this is important. This was asked, similar type of question was asked in NEET 2019 Odisha paper as well. So these are the reactions of alkyne. With this, we are concluding the theory part of alkynes. Let us now quickly discuss some of the important questions which is related to alkenes and alkynes. Question number 1. An alkene A on reaction with ozone and zinc in the presence of water gives propanol and ethanol in equimolar ratio. Addition of HCl to alkene A gives B as the major product. Structure of the product B is. So here we have to use two reactions at the same time. So it's a very important question which is asked in NEET 2019. Let us see how to solve with such type of questions. An alkene A is reacted with ozone and zinc in the presence of H2O. That means we have the process of ozonolysis. The products of ozonolysis are given, that is propanone. So let us arrange propanone like this: CH3, CO, CH3. And I am going to arrange ethanol as CH and CH3. Now let us put the other oxygen so that we can get an ozonoid like structure, and let us bring our terrorist here, and so that they create a war and destruct the home. Now we have the war zone, we are going to remove the war zone. All the war zones are removed. Now both the enemies are on the either side. Now let us separate them using a bridge, and the bridge is a double bond. Now we get a compound like this. What is the next step? We have to add HCl. Hydrogen should be added to this side according to Markovnikov's addition, and chlorine should be added to this side. So option C is going to be the answer. Sorry, we have to carry out the opposite way. Chlorine will come to this side and hydrogen will come to this side according to Markovnikov's addition. So the answer is option number C. Now let's move on to the next question, which is a theoretical question. We have to create cis-alkene. Cis-alkene is created from alkyne, so we have to use Lindlar's catalyst, that is hydrogen in the presence of palladium or quinoline. Now here what we have to do, we have to calculate the number of sigma bonds which is present in the product A. So what will be the product? The product is not benzene. We will be getting 3 CH3 groups as well. This is the product that we are getting. You have to calculate what is the number of sigma bonds over here. So that is a DIY for you. We have to calculate what is the number of sigma bonds. You have to comment the answer below. Comment. Now let us do the next question. The question which I have told you before. What is the correct order of acidity? First will be alkyne. So either this can be an answer or this. So we have to consider the second one. Once we consider alkyne, next we have to consider the number of carbon. 3 carbon containing alkyne is also there. 2 carbon containing and 3 carbon containing is there. So 2 carbon containing will be more acidic because it is inversely proportional to the number of carbon. So this is going to be the answer. First 2 carbon and then 3 carbon, and then comes alkene and finally comes alkane. Now this is a complete the reaction type of question. So let us see how to solve this question. First step, we are going to treat it with NaNH2 in the presence of liquid ammonia. So when we are treating it with NaNH2 in the presence of liquid ammonia, we get CH triple bond CNA. That is, a sodium gets substituted at this position. Now that is reacting with CH3CH2Br according to the question. So what is happening? NaBr is eliminated out and this alkyl part is substituted over here instead of sodium. Now we are going to carry out the reaction with NaNH2 again. So it is substituted to the other side, that is this side. And now again we are adding CH3CH2Br, so that is getting substituted in the place of sodium. So this is the final product that we are getting. Easy question. Now which of the following reagents will be able to distinguish between 1-butene and 2-butene? It is NaNH2 because NaNH2 will react with terminal alkenes only. It will react with terminal alkynes only, and so it is going to react with 1-butene only, and 2-butene will not give the reaction. So this is a question from NCERT. An alkene A on ozonolysis will give us a mixture of ethanol. So let us make the structure of ethanol here, CH3 and H, and pentan 3 on, so it is C, C2H5, C2H5 and C double bond O. So this is the structure of the two compounds that is given in the question. We have to find what is the structure of alkene. So create an ozonoid and do the cleavage, remove all the war zone And now what we have to do, we have to just create a bridge. So this is the alkene that we are getting. Find out the structure of the alkene, which on ozonolysis will give us these products. Now whenever we have carbon dioxide in the question, always keep the carbon dioxide in the middle like this, and C6H5 C6H5CHO. So let us keep it like this. We will put an oxygen here, and this oxygen is attached to a carbon, and on the carbon we have C6H5 and a hydrogen, and on the other side we have CH3 and a hydrogen here. So we have to remove this oxygen, we have to remove these oxygens as well, right? And now what are we getting? We have CH3 CH double bond C double bond C H C6H5. This is the compound that we're getting. We're getting an alene type of compound. Let's do the next question. Propanal and pentan 3-on are the ozonolysis products of propanal. So it is going to be CH3 CH2 CHO, and we have pentan 3-on, so we have C double bond O, C2H5 and C2H5. Create the ozonide, break the bonds, remove the Warson, and now create the bridges. So this is the compound that we're getting. An alkene A contains 3 carbon-carbon bonds, 8 carbon-hydrogen bonds, and 1 carbon-carbon double bond. A on ozonolysis gives 2 moles of an aldehyde of molar mass 44U. So let us take the homologous series of aldehydes. The first member is HCHO. Obviously HCHO will not have 44U. But if we consider CH3CHO, we can identify that its mass is 44U. So we can say that the aldehyde of this question is CH3CHO, and we are given 2 moles of this aldehyde. So let us take 2 moles here. That is CH3 C double bond O single bond H, and another molecule of, so I will put the hydrogen to this side, and we have C double bond O H and CH3. Let us create the ozonide, cleave everything, and we will rub off the unwanted people, and let us create a double bond in between them. So now we are getting this particular alkene. So here we can see there is 3 carbon-carbon bonds here, and we are having 8 carbon hydrogen bonds and 1 carbon-carbon double bond. The catalyst which is used to reduce an alkyne to alkene is, the answer should be Lindlar's catalyst, right? Now let us move on to the next question. We have this compound, we have to add this. What is the example? It is an example of nucleophilic addition. This is a rare case where we have nucleophilic addition, so we have to study this. It's important. Now this is a question based on Kolb's electrolysis and also decarboxylation. We have acetylene, sorry, not Kolb's electrolysis, it is based on KMNO4. So this on oxidation, this bond is going to cleave and we will be getting acetic acid, and this acetic acid is now undergoing decarboxylation, so it will give 1 carbon less, so we will get CH4. Question number 17, Mg2C3. Mg2C3 will give us a compound that will have 3 carbon. So the compound C will be having 3 carbon. So this is wrong. Now C has a terminal CH3 group, so it will give tolerance test. But we have to find C. I am talking about A. So let us first treat it with sodium. So when we are treating it with sodium, we get this compound. And finally, when we are treating it with CH3Br, we will be getting this compound. So this is not having a terminal alkene, so it will give us tolerance test. It does not contain an acidic hydrogen, so it will give us tolerance test. That is incorrect statement, right? That is the incorrect statement. Now let us move on to the next question. So here we have to add Hi. So this is basic mechanism type of question. We have to add hydrogen to that side which is deficit of hydrogen. Sorry, it is according to Markovnikov's addition. So we have to add hydrogen to that side which is having more hydrogen, and which side is having more hydrogen. Here both sides are having same, so we have to look for stability. Now when we are considering stability, we can say we have to add the iodine to this side and hydrogen to this side, because the number of hyperconjugation structures is more in the case of this side. So the answer should be 2. Now this is the last question for today. The minimum heat of hydrogenation is in. So first of all, we will write down the products A and B. A is coming out to be the cis form, and A is coming out to be the trans form because we have used Birch reduction, and B is going to be the cis form because we have used the Lindlas catalyst. And since we know transbutane will show minimum heat of hydrogenation because trans is more stable as compared to cis form, so we can say the answer should be 1. Now this is a very simple question. In which of the following reactions Markovnikov's rule is not observed? As we can see here, this is peroxide, and here also there is peroxide. So whenever peroxide is there, Markovnikov's is not followed. We have Karash effect, so it is 4. Now this is a question for you to think and be patient and do this question. You have to carry out ozonolysis at 3 positions of the double bond. Right? So here we have to take both the isomers of benzene and carry out the process of ozonolysis. And when we are taking the ozonolysis, we get all these products. So take your own time and do this process. Although it looks a bit confusing, but make a beautiful diagram and then it will be easy for you to solve. So this brings us to the end of this lecture. So we have completed alkanes, alkenes and alkynes in the 2 parts. In the next part, we will be discussing about the aromatic compounds, and we will be also discussing some of the important questions from NCERT exemplars as well as NCERT exercises based on the chapter hydrocarbons, and we will be finishing off this chapter. So see you again in the next lecture. Till then, goodbye and happy learning.